Hi guys, it's Miss Hill here with our first lesson about linear equations. Going back to Math 1, thinking in context, can we get the information from the problem, use that to write a now next rule, and then use our now next rule to write an algebraic rule? So we will start with our first example. An electronics store has 20 CD players on the shelf. They also have boxes of these CD players in the back room. Each box contains 12 CD players. We want to write a linear function that relates the total number of CD players in the store to the number of boxes. So let's start looking at the information they gave us in the problem. First, we notice that there are 20 CD players on the shelf. So those are already out in the store for anyone to come in and purchase. They also have boxes in the back room. Each box contains 12 CD players. That's going to be important. So as we're going to write our equation, we can set up a table. You can always do this for any type problem. Set up a table and look at what we know and what we can figure out from there. So without having any boxes in the back room, we know that there are 20 CD players out on the shelf. If we have just one box in the back room, we have our 20 CDs plus another 12. So we're going to add 12 to the 20 that are already on the shelf, and that puts us up to 32 CD players that are available in the store. If there were two boxes, we're going to add another 12 because that's another 12 in a box, and that puts us up to 44 CDs that are available. If we have three boxes, that's going to put us up to 56 CD players available. Four boxes would bump us up to 68. 5 boxes would put us at 80. And then 6 boxes would put us at 92 CD players that are somewhere in that store. So looking at this, we want to write our now next rule. And we can see that wherever we are now with each additional box, we're going to be adding 12 CDs. So that means we're going to say our next is equal to where we are now plus the 12 CDs in each box. But we want to start with the 20 CD players that are already out on the shelf. So now we can relate the total number of CD players that are in the store to the number of boxes by saying that total number of CD players in the store is going to be equal to 12 times the number of boxes plus the 20 CDs that were already out. And this can be used to help us define our variables. We can say that the total number of CD players depends on the number of boxes that are in the back of the store. So keeping in mind our dependent variables are the y, so we're going to let y be equal to the total number of CD players. And then we're going to let x be the number of boxes. That's our independent. So now we can use that to write our algebraic rule. Y, the total number of CD players, is going to be equal to our 12x, 12 times the number of boxes, plus our starting point of 20 CD players that were already out on the shelf. Now from our rule, we can graph all of this information using the table and or the equation. We know that we start with the 20 CD players. If we add one box to the mix, then we're up to 32 CD players, which would be about there. There we go. And then if we have two boxes, we're up to about 44, about there. 3 boxes puts us at 56, so we're not quite to the 60 mark. 4 boxes puts us at 68, about there. 5 boxes, we're up to 80 CD players, and 6 boxes, we're up to 92. And then we can connect those points with the nice straight line showing that yes, we do have a linear function. And then we also want to make sure that we understand what's going on with the domain, range, degree, and end behavior. So keep in mind, domain, we're talking about the x values that we can see from the graph. And we can see that our x values in the graph are greater than or equal to 0. We could have 0 boxes. That's possible. For the range, we're talking about the y values that we see in the graph. And our y values are going to be greater than or equal to 20. We're starting at the 20 CD players that are on the shelf. Now, we mentioned that this is a linear function, and with any linear function, the degree will always be 1. If you look back at that algebraic rule that we wrote, the degree comes from the exponent next to the variable, or I should say the largest exponent that's in our equation. So if we just have 12x plus 1, it's understood that we have that exponent of 1, so our degree is 1. Then the last thing we're going to talk about today is the end behavior, what's going on with our graph. So as our x values approach the negatives, as our x values over here are decreasing, we're getting smaller and smaller, same thing is happening with our y values, except our y values are going to stop at 20. So that means that our y value approaches 20. On the other hand, as x is getting larger, it's getting bigger and bigger, then our x values are also increasing, and it can keep on going forever. So we're just going to say that y approaches positive infinity. All right, let's get a couple more examples in here. For example 2, very similar. We have a cab company that's charging $3 just for getting into the car. So the boarding rate is $3 and then $2 for every mile that's traveled. So there's our important information that we need there. And we're going to do the same thing. We're going to write a linear function that relates the cost of the cab ride to the number of miles that are traveled. So again, from the problem, we know it's $3 just to get into the cab and say, I need to get to this place. Then for each mile, we're going to have to pay another $2. So that means that we're increasing by 2. Oops. So when we add 2 to the 3, that means our total is going to be up to $5. For 2 miles, we're going to add another $2, so we're up to $7. 3 miles, it's going to cost us $9. 4 miles would be $11. 5 miles would be $13, and 6 miles would be $15 for the ride. So putting that into our now next rule, we can say that our next is equal to where we are now, plus that $2 for each mile, and we're starting at the $3 just for the boarding rate. So putting that into words, the cost of the cab ride is going to be equal to 2 times the number of miles. Then don't forget we also have to pay that extra $3, so it's plus $3. So now from our now next rule and putting everything into words, we can say that the total cost of that cab ride depends on the number of miles that we had to drive. Again, our dependent variable is the y, so y is going to be the total cost. And the independent, or the x, will be the number of miles. So writing that as an algebraic rule, we have y is going to be equal to 2x plus 3. Now we can use our lovely table or the rule to help us graph. We know that we're starting at $3. So halfway between the 2 and the 4 would be our 3. And then it's $2 per mile, so 1 mile we said was at 5. And then 2 miles is up to 7. 3 is up to 9. 4, we're up to 11. If the pin were right, there we go. And then 5, we're up to $13. And then 6 miles, we're up to $15. And again, we can see here that we have a nice straight line, another linear function. So since we have a linear function, we can go ahead and say that our degree is 1. For our domain, the x values that we used for this particular problem, we would say that x is greater than or equal to 0. We don't have to drive anywhere. But the range, we're paying that $3 to get into the cab, so it's going to be y is greater than or equal to 3. So our end behavior, as x approaches the negatives, as it's getting smaller and smaller, our y values approach that 3 that we know we're going to have to pay to get into the cab. But then, if we're going into the positives, we can go forever and ever. As long as you want to ride in that car, they're still going to take your money. So y is going to be approaching positive infinity. All right, so now let's look at example 3. In example 3, we have our Electric Avenue that sells our audio and video, computer, and entertainment products. So they offer 0% interest for 12 months on purchases that are made using their particular store credit card. So if Emily goes and purchases a TV for $480, we want to see how is that balance going to be panning out over the next year as she makes those monthly payments. So now if we look at her table here, starting out with her $480 that she starts out owing, after 1 month she's down to $460. So that means that she's paying $20. So she decreased the amount she owes by $20. Looking at month 2, $460 to $440, again she's reducing by $20. This happens for every single month, reducing by $20. She paid another $20, another $20, and another $20. So this lets us see that yes, there is a constant rate of change. It is a linear function because there is a constant rate of change. And we can see that each month she's decreasing by $20. So since we have a linear function, we have that constant rate of change, we can say that we do have a now next rule, where next is going to be equal to now minus 20 because it's decreasing by $20 a month. And we started at $480. So some of you might easily be able to see without writing the now next rule that we can write the algebraic rule that y is going to be equal to negative 20x plus 480. So keep in mind that decrease of $20 per month, that minus 20, there's your slope, which we use m to represent slope. And wherever we say we're starting at, that's your y-intercept or the b value. So eventually we are going to get away from writing the now next rules and go straight to the algebraic rules, but for now we're going to use both. Now we can use our algebraic rule to determine things like, will Emily pay off the balance within 12 months? Well, 12 months, remember we said x is the number of months. That's our independent variable. So if we let x be 12, then we can use our rule and say y equals negative 20x, or 20 times 12, plus 480. Well, that negative 20 times 12, that's going to put us at negative 240. So at the end of those 12 months, she still has $240 to pay off. So no, she has not paid off the $480 that she paid for the TV in that first year. So this is what she still owes. All right, let's look at one last example, making sure that we understand the now next, using that to write our equations and exactly what everything means within our equations. So looking at example 4, the average lifespan of American women has been tracked, and the model for the data is Let's put the y equals over here with the rest of it. We have the equation y equals 2/10 t plus 73, where y is the lifespan and t equals 0 corresponds to 1960. So kind of going backwards from what we've been doing. Remember, our slope tells us what happens to the now. So we can say now plus, since it was positive, 2/10. And then at the very end, that plus 73, that's where we start our y-intercept. So starting at 73. So we just said that our slope is at 2/10. If we want to relate it to the context of the problem, our problem is talking about the average lifespan of American women. And that was starting in 1960. So we're looking at how the average lifespan of American women increases over those years. Well, if our slope is 2/10, then it's increasing by 2/10 of a year every year. So the average lifespan of American women we have a positive slope, so it increases by 2/10 per year. So each year, women tend to live about 2/10 of a year longer than they did the year before. Then for the y-intercept, we said our starting point was at 73. Well, remember we said this data started being tracked in 1960. So that means back in 1960, the average lifespan of American women was 73 years old. So the average, I'm just going to abbreviate, the average lifespan of American women in 1960 was 73 years. And again, we can use this to make predictions and see what would happen or what we could expect to find the lifespan of a woman here in America in 2015. Well, first we need to see how many years was that since they started tracking all this data in 1960. So we're going to subtract 2015 minus 1960 and see that that was 55 years ago. So that means in our equation that we were using to model this with y equals 2/10 t plus 73. This means that since it's been 55 years, t is going to be 55. So when we plug that in, y equals 2/10 times 55 plus 73. Well, 2/10 times 55 is going to give us 11. And 11 plus 73, we would expect the average American woman to live to be about 84 years old. And there we go. So you have a couple more examples in your packet, and then you also have 10 problems to do for homework tonight in your packet. You may check those answers on Blackboard. Feel free to email or send a remind message if you have any questions. Thanks, and I'll see you tomorrow.